Please welcome William Hutton. He's going to teach us how to teach computers to fight themselves.
Yeah. Thank you. All right, so I'm always curious about the experience of my audience, and this is a large enough room that I don't want to make assumptions about what you know, so just by a show of hands, if I could see who has played the game of Ogre before? A couple of people. I will explain what it is, so we don't start from the beginning and everybody's lost. How about artificial intelligence? Anybody played around with that a little bit? More people, a lot more people, excellent. Any philosophy people in here? One, okay, excellent. So it gives me, and how about Python? I was going to do this as a novice introductory talk. I didn't want to assume anything. I think it's hopefully an interesting topic. But beginning Python programmers? Am I the only beginning Python programmer? Okay. All right, so let me go ahead and get started here. But just in a broad sense, we're going to obviously talk about the board game Ogre. We're going to talk about machine learning, artificial intelligence, specifically genetic algorithms. We have to talk a little bit about Aristotelian ethics. So we'll back up just a little ways to about 500 BC. And then we'll jump forward again and look at how I did this with Python and more importantly, probably why. So I came across a great quote on the airplane on my way out here. If anyone's reading Ernest Cline's new novel called Armada, this is the very first thing in Armada. And so, and you'll notice that Jarvis didn't say video games. He said games. So, does anyone know what the first computer was? We can have a little bit of participation. You can shout it out and I'll repeat it. Not necessarily the first game, the first computer. Yeah, so you can go way back to mechanical computers that could only solve one problem, right? If you wanted it, we didn't get to a repeatable use of a computer till John von Neumann had the von Neumann architecture. But early on, the first computers were actually people, and they were called computers, and they used slide rules to calculate tables for artillery. And there weren't enough of these books in, I want to say World War II, at the beginning of World War II. So the first computers were actually people, and people make mistakes, we're slow. Computers, digital computers, are much better at solving well-defined problems than we are. They can do it much faster, and they can do it without error. Does anyone play Magic the Gathering? Know who Mark Rosewater is? Okay. So Mark Rosewater asked a question in one of his podcasts, what's the difference between a toy, a game, a puzzle, and sports? And since we're all here at a Python convention on Saturday, let's not even attempt to tackle sports. No idea. Okay. A toy is something you play with for fun. A game, let's think about what a game is. A puzzle is usually something you're trying to figure out, and a game usually has some type of a goal. So let's take a look again at another popular reference. Joshua from the movie War Games was an artificial intelligence that played games. And this is sort of my first introduction to computers is about this era. So my first computer was a Commodore 64. Anybody not seen War Games? Because we could just stop the presentation now and have some remedial hacker training here. So definitely go see War Games if you haven't seen it. But the whole premise of War Games was an artificially intelligent computer playing games of strategy to learn how to apply that strategy to better, in quotes, play nuclear war in real for the military. So the neat thing about artificial intelligence is that the computer can play the game so much faster than we can. If you and I were to sit down, Ogre's a two-player game, so if you and I were to sit down and play a game of Ogre, it would take us between 30 and 60 minutes. And if we just average, it would take about 45 minutes. So in that 45 minutes, you and I could play one game of Ogre, and one of us could learn a little bit about the complexity and the strategy of one side of the game, the defender. The AI that I wrote in Python can play about 100 games of Ogre in 30 seconds. So to put that another way, in the same amount of time it would take us to play one game of Ogre, my Python AI can play about 9,000 games of Ogre. So there's a lot more opportunity to learn. There's a lot of learning that can happen as you play the game over and over and over. To put that another way, if you and I played Ogre and we wanted to get 9,000 games in and all we did was play Ogre, we didn't eat, we didn't sleep, we didn't do anything else, it would take us just over 281 days. So it's really nice to be able to have a theory and test your theory out in Python, which is great about Python. Python is considered a rapid prototyping language. So if you're a computer scientist, that means you can get your prototype of your software built much more quickly. But if you're a regular scientist or a non-computer scientist, the beauty of Python is that you can have an idea and you can you have a hope of getting your idea into code and being able to do your own experiments without necessarily being a computer scientist, which is pretty neat. So the reason I did this was board gaming is one of my hobbies, and I took a Python class last fall. I've written in other languages. I'm a software developer, and I naively thought that the differences in Python were just syntax. That since I know C++ and I can code in C++, I can figure out Python. And I tried Python in starts and fits 2 or 3 times and decided I absolutely hated the language for 2 little reasons. And if you guys love Python and you know why people like and don't like Python, you could probably guess, right? White space matters, drives a structured programmer crazy, and there's no statement blocks. No curly braces to show, in an if statement what gets executed and what doesn't. And it turned out that all the Python code I wrote, I wasn't using the Python paradigm. I was using other programming paradigms, so the Python I wrote was very procedural. It worked, but it was what we would call very un-Pythonic. And I really wanted to learn the right way to do Python because I am a scientist in my day job, and we do a lot of experiments that involve computers. So I took a Introduction to Python class at Washington State University from Bob Lewis, and I learned a ton. A lot more Python than I could ever learn from just reading a book, even though I've been programming for decades. So if you get the chance to study Python from someone who is very good at Python, by all means, take advantage of that opportunity. So part of our coursework was to write a term project. Make your, you've learned Python, now make Python do something for you. So the first day of class, I thought, well, why don't I teach Python how to play my favorite board game, Ogre? Because Ogre's complicated and I haven't figured out how to solve it. Let me have a computer solve it. That was biting off way more than I could chew in the beginning. If you ever have to do a term project, don't be that ambitious. Because I worked a lot on this. But it was very much a labor of love, so I'll show you guys what that looks like. Before we go any further, the source code is available on GitHub. This is in general. If you're going to do any kind of presentation or even just writing a paper, share your data and share your code so that other people can experiment with it and play with it. It's much better than just seeing a presentation or reading a paper. Put your data out there so people can use it as a stepping stone and a jump-off point. It's very easy to run. If you just run setup.py install, it'll install everything for you, including the MySQL connector. It will not install MySQL for you, though. So that's the only prerequisite, is that you have MySQL. It will create the database. It'll create all the database schema and structure. It'll insert all the data you need. And this is a console application, so you can play around with a console. There's also a lot of development work we could do if you want to help contribute to the project. So let's talk about the game of Ogre itself first real quick. I brought the original Ogre game. If you can see it, it sold for $2.95 in 1977. Came in a Ziploc bag. It did not come with the die you need. You only need one die, one 6-sided dice. It's called a hex and counter war game. It's a light war game. So the counters are little pieces of cardboard that represent the units. The map is a hexagon map which later when I talk about the approach, the shape of the map is actually very hard to represent in Python. So we'll talk about that. But this is the original game. Very portable, very tiny. In 2012, Steve Jackson Games launched a Kickstarter campaign to make a new version of Ogre, and that's Sam Healy hiding behind the 26-pound box that is the new version of Ogre. Literally could not bring it on the plane even if I wanted to. Does not fit, and I'm not going to check it. So they raised over $1 million. It sold for about $100 a box. And kind of an interesting thing is they lost about $300 per box that they sold. They offset the losses with Munchkin. So if you play Munchkin, thank you. So that's Ogre. One thing to know about Ogre is that it's asymmetric. And when we're talking asymmetry in warfare, we're talking about a disadvantage or an imbalance. Now, Ogre is also a game, so it wouldn't be fun to play an asymmetric game because one side would always lose, and that's not fun. The rules are very simple, and the strategy is very complex. So just briefly, this is an Ogre in the bottom left corner of the screen. It's a 3D piece of cardboard in the fancy Kickstarter version of it. And this is the attacker. So if we played a game and someone's the attacker gets the Ogre. The defender gets everything else you see on the board. And the very top corner, just about off the map where you can't quite see it above this last counter, is something called a command post. The defender is trying to preserve their command post. The Ogre is trying to destroy the command post. There's a mix of infantry and armor units that are represented by these black counters. There's ridges that you can see. The infantry can jump over the ridges. The Ogre can drive over them. It doesn't care. It's massive. It's a giant armored tank, artificially intelligent with nuclear weapons. It's an awesome weapon. These are regular infantry, regular tanks. They don't stand a chance, but you get a lot of them. And the complexity of the game comes from trying to figure out what units do I take, where do I put them, how do I move them, how do they join and combine fire, and what do I target on the Ogre to win. And remember, it takes about 30 to 60 minutes to play a game, so the first couple times you play as the defender, the game consists of the Ogre driving to your command post and crushing it and then exiting off the other end of the map. So there's a lot to figure out there. All right, so a little I don't want to give a whole presentation on Ogre, but we have to understand a little bit about it so we can talk about the Python code. So this is a counter. This is an armored unit called a missile tank. It has a attack strength, which is 3. It has a range, which is a 4. It's got a defense value of 2 and a movement value of 2. So it can move 2 hexes and then fire. And when it fires, it's basically got a strength of 3, and it can reach up to 4 hexes away. And then the howitzer is another example of another type of armored unit. It's got a movement of 0, so it doesn't move. It's got an attack strength of 6 and a range of 8. So if something was close enough that was in range of the missile tank, it's also in range of the howitzer. And they could combine their firepower if they wanted. This is what the Ogre looks like. The Ogre has a lot of different weapons. It's got a main battery, 4 secondary batteries, 2 missiles, 8 anti-personnel weapons. They all have different attack strengths, different ranges, different defense values, and there's also tread. If you think about a tank, there's the tread that lets the vehicle move. Even if you knock out all the weapons on the Ogre can still kill you by just driving over you, and it loses like 1 tread, and it's got 45. So as a defender, the main battery does the most damage. You can focus on the main, but it's got all these secondaries. It's also got missiles, so it can go reach out really far. And like I said, even if you knock it out, it can still drive over you. So if you just focus on the tread are actually pretty hard to kill, and there's 45 of them. So by the time you knock out the tread and it gets to 0 and now it's stationary, now you still can't get very close to it because it's still got all these other weapons. So there's a lot for a gamer to try to figure out what's the optimal strategy here. So again, the game is asymmetric. And in game terms, asymmetric meaning different, not unbalanced. The defender is going to get a choice of 12 different points of armor units, and that's generally each unit costs 1 point. It's not the attack strength. And then you're going to get 20 points of infantry, so you're going to get a lot of counters to try to figure out how to spread them out on the map. And then, as I said, the complexity is what units do you pick, where do you put them, how do you use them, and what do you target on the Ogre to try to knock it out. And so this is basically what we're going to try to teach the computer. And the question is how do you teach a computer to solve this problem when you yourself don't know how to solve that problem? So we have to understand a little bit about the example of combat, and then we'll be done with the rules of Ogre. So the main method of resolving combat uses a very familiar thing if you play war games called a CRT, or a combat results table. You're basically going to look at the attack strength of the attacker, and you're going to compare it to the defense strength of the defender. You're usually going to get a ratio. Then you're going to roll a die, cross-reference the ratio to the result on the die, and you have your outcome. This is just an example here of the Ogre and a unit. The disabled tokens just show you the range of that weapon. So the Ogre is out of range of that weapon. So the armor unit there called a GEV would have to move towards the Ogre to get in range and shoot it. It's also by itself, so it's probably not going to actually hurt the Ogre. This is the combat results table. The green NEs stand for no effect. So things have armor. So if the attack strength is too low or unsuccessful, there's no effect. The yellow D is disabled, and the red X is destroyed. And when it comes to targeting the Ogre ignores Ds. So you can't disable the Ogre. You can only destroy it. And you can only destroy the particular system you're targeting. So if I'm trying to target the Ogre's main battery, which I think has a defense of 3, I need an attack strength of 3 to come up with a 1-to-1 ratio. And then when I roll the dice, I have to roll a 5 or a 6 in order for it to be a success. So generally, I have to pool my attack strength. And then I have to also target the right thing. And then I also have to get lucky on the dice. The Ogre's pretty tough to fight. And one last thing is the victory conditions. The victory conditions are important because when my Python AI plays a game of Ogre, it needs to know how well it played. And there's going to be a notion of a complete defense victory. And just so you know, my training data, which we'll talk about, I had the computer play 100,000 games. It never had a complete defense victory, which is probably a shortfall of my AI approach, which we'll look at in a minute. There was also never a complete Ogre victory, which is nice. So the bold and underlined things were the types of outcomes. A defense victory just means that the command post survived and the Ogre was destroyed. A marginal defense victory means the command post and the Ogre were destroyed. That's still a victory for the defense because it's that hard to kill the Ogre. A marginal Ogre victory is, I got that backwards. The marginal defense victory is the command post survives and the Ogre escapes. A marginal Ogre victory still has the Ogre being destroyed. And then an Ogre victory is the Ogre not being destroyed. It drives up, kills the command post, and exits the board to the south. And then the complete Ogre victory is it kills everything. That thankfully never happened. So that's how you play Ogre. Any burning questions about Ogre before we move on? Okay. So let's talk Aristotelian ethics and why this is important in warfare. So Aristotle wrote a book called the Nicomachean Ethics for his son, who was named Nicomachean. It's the Nicomachean Ethics. My Greek is not very strong anymore. My undergraduate degree is in philosophy, though, which is why I decided to get interested in artificial intelligence. So Aristotle has a value in his ethics of what he calls temperance, or what we would call moderation. You might have heard moderation in all things. That comes from Aristotle. So there's a continuum of values or behaviors. And if you're too far to the left or the right, you're basically not where you should be. Okay, so if you examine a unit in war, being cowardly is obviously not a good trait. But being brave is also not a good trait. If you just, go over the wall, guns blazing, and attack, especially an ogre, you're just going to get squished. You have no hope of hurting it. So somewhere along this continuum is an ideal of what we'll call disciplined. You're not too brave, you're not foolhardy, but you're also not cowardly either. You're disciplined, right? That's what we want to be. So when it came to programming the defender's units in Ogre, I took these three, what Aristotle would call values, and implement them in the game. So brave units are going to behave differently than cowardly units or disciplined units. A brave unit will find the ogre and pursue it. If you think about AI in a game, it will pursue you. It's pursuit AI. And it's got something called probabilistic targeting. It's going to favor targeting the most threatening weapon, but not always. So 50% of the time it will go after missiles or the main battery, which are the most threatening weapons. But 25% of the time it may go after a secondary battery, or it might go after tread. This is important because I wasn't sure which thing was the right thing to target on the ogre. And so I wanted to have some randomness in there, that when the game was done, I could go back and I could see what was targeted by the brave units. But bravery might not be the right value in terms of how our units behave. So I also wanted to have cowardly units that flee the ogre, which is, they have a notion of self-preservation almost. And what they do is, the way they flee, they don't just run away from the ogre because they're still a military unit. They flee the ogre towards the command post. So what you'll end up with is the command post ringed by armored units, which makes the ogre have to drive over them, which destroys its tread. They basically shut their eyes and point in the general direction of the ogre and pull the trigger. They target randomly because they're cowards. They just sort of shoot in the general direction of the ogre. And they are uncoordinated. They don't work together. Because who knows? This may be the right way to play the game, right? We don't know. So this is another unit behavior. And then disciplined is a mix of the two. So they don't flee, but they don't pursue. They will target the ogre's weapon systems in order of the most threatening to the least threatening. And they will also try to combine their firepower at 3-to-1 odds. The reason that we go for 3-to-1 is that 2-to-1 odds is only going to give you a 50-50 chance of destruction on that CRT table. And I wanted better than 50-50. So those are the how Aristotelian ethics is applied to the units in AI when they attack each other. So now that we have a way for the units to behave, and I've modeled the Ogre rules using Python, we need a way for the computer to learn from its games. How is it going to, we don't just want it to play randomly. How is it going to get better? And how is it going to judge that it's doing better? And the way that we do that is with a machine learning technique called a genetic algorithm. And I'm going to use something called a genome, which is just a description of the genes that make up an organism. So in this case, if we think of the game as a living organism, there's a sequence of genes that define that game in terms of the units that were used to play it and their behavior. And then each individual unit is also going to have a genome. It's going to be much smaller, and it's going to include its behavior. We've got our 3 behaviors that I modeled: brave, cowardly, and disciplined. And then we have a unit type. The howitzer is just identified by an H. So a brave howitzer is identified by a genome of BH. And if we had 4 brave howitzers in our game, the genome of our game would just be BH, 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 BH. So the way genetic algorithms work is you have parents, and those parents have offspring. And in this case, if we take a brave howitzer and a disciplined heavy tank, which is what the Y is, the Y stands for a heavy tank. If these are the parents, these are the possible children those 2 parents could have. So we could inherit both of our genes from parent 1 and get another brave howitzer, or strictly using genes from parent 2, get a disciplined heavy, but we could also cross genes. And so I could get a disciplined heavy or brave, or sorry, a disciplined howitzer or a brave heavy. Everybody tracking on that? Question? Okay, this is a great question. The main reason is space, right, and computational time, right? It's basically it. I don't want to say it's NP hard or NP complete because I don't know and I haven't done the proofs. Oh, I'm sorry. Yeah. So the question was why use this approach instead of a brute force approach of picking every unit and assigning every possibility of every unit to every behavior and playing the game. And the reason is the space complexity. It's just too high. So what we do is we start randomly by selecting some number of units within the rules of the game of 12 points of armor. And there's a probability of homogeneous units and heterogeneous units. So, and I'll get into this when I look at my training data, but you may start the game that way with all howitzers, and then all heavy tanks, and then all light tanks, and then all brave, all cowardly, all disciplined. But instead, we look at that as a probability for unit selection and discipline, and then we just play the game and see how well they did. And at the end, when we rank the games, we rank it by those victory conditions, and then we use number of turns and the condition of the ogre to break ties. So there's a way for us to evaluate how well a choice of units behaved. So this is that genome sequence of an individual game. And once we've played 2 games, what we can do is we can use those games as parents, and we can begin to construct new genetic sequences for future games based on the previous games. And of course, we're going to rank the games in the database by how well they did in terms of victory conditions and how destroyed the ogre is and how many units we have left, so that we're only picking sequences from what we'd call good games. So that's a good question. The ogre is complete victory for the ogre. He may decide to drive around and knock out units first. In terms of the AI for my ogre, it just drives straight to the command post. It will try to reserve 1 missile, so it doesn't have to go all the way to the command post, because the missile is the longest reaching weapon. And once it destroys it, it will not seek and destroy the other units, which is why there was no complete ogre victory. So basically drive to the command post, kill it, and flee. And right. This is also, remember, a term project for an intro to Python class. So, and I did not know Python very well when I started it. So in terms of future work, though, different ogre strategies is absolutely legitimate. Different behaviors for the units, and there's a lot of room here, obviously, to play better. But in terms of how it comes up with new unit selection and new unit behaviors for future games to play, it could take some DNA from the left side of both parents. It could take some DNA from the right side of both parents, or it could cross-pollinate either direction like this. So it will take these gene sequences from the, what it does is it will it'll select the top 10 games that were played out of the training database. It'll pick 2 at random, and then it will cut the DNA like I show you here, and then it will pick 2 of those sequences at random. Once it's got a new string for unit selection, and there's a little fudging we have to do on this, because these sequences could break the rules in terms of how many units you're allowed to take. Because a howitzer will count as 2 units. A regular tank counts as 1 unit, and a light tank counts as half a unit. So once we have a new sequence, we've got to go through that string and optimize it to make sure we're playing the rules, or playing the game by the rules. But here we have a new sequence for a new game, and we're going to try this sequence out. But one last thing that can happen in genetics is mutation. And there's a configurable property in the code. Right now it's set to a 5% chance of mutation. And to your question again, how do we know this is the right strategy? That 5% might not be the right value. We might need to lower it or raise it. But there's a 5% chance that any individual gene is going to mutate. So as you can see, we started off with a brave howitzer, but it mutated to a cowardly howitzer. The mutations are shown in white. This is a look at the game loop. And some of it's pseudocode, some of it's just little code snippets so you can see what I was doing here. First thing you do is create the map. The map is, I naively thought you could represent it in a 2D array. But when you look at the hexes, a hex has 6 sides. It's not a square. So it doesn't have a neighbor, it doesn't have orthogonal neighbors, north, south, east, west. It's actually got a neighbor to its north and its south, and then it has 2 neighbors on the east and west, a northeast and a southeast. And different hex layouts have different neighbor schemes depending on if they're pointy-topped or flat-topped, the rotation of the hex. And to make it even more fun, if you look at the whole Ogre map, the hexes are vertically offset. So the first column might be low, and then the second column is actually higher. So it's jagged along the top and bottom. So it's a very weird 2D array if you try to represent it as a 2D array. Once we have that map, we go through and we add the craters. The craters are impassable to everyone. So in terms of the Ogre finding its way to the command post to destroy it, it has to figure out how to navigate around craters. And then it also has to figure out how to not drive towards dangerous units. So there was a lot of AI pathing that I had to implement using an algorithm called A-star. So you can take a look at that algorithm. I didn't ever find any Python code for A-star, so I had to write my own, which took longer than I would think, but it was a introductory class again, so it took a while. We have to add the ridges in, and then the way we basically play the game is that we need a certain number of games to learn from that are going to be our training data. I picked 100 games. That may or may not be the right number. When it goes to play a game, if there are not 100 training games already in the database, it will just pick units at random and play the game until it gets to 100 games. And once it's reached that 100 games, then that genetic algorithm I showed you kicks in. And then it starts trying to figure out what were the best games I played with the best unit selection and behavior and learn from those games. And then the question was, did the computer even learn? And we'll look at that in just a second when we look at the data. I explained how the genetic algorithm works there. The results go into a MySQL database, and then if you just tell it to play a game, it'll play a game. And I'll show you what the output looks like. If you tell it to play n games, it'll play 100 games or 1,000 games, or I think about 2 days ago I told it start playing 100,000 games because I wanted a large set of training data for the presentation today. So the Python code, if you look at it, it's got 2 constants in every module. It's got a debug Boolean that you can set to true or false, and it has a interactive Boolean. So if you turn debugging on and turn interactivity on, it will dump a lot of data to the screen, and then it will pause and wait for you to hit the enter key. This was important because as I implemented the rules, I had the large cardboard game set up next to me so I could see what it should be doing and I could debug the code. So, is the Ogre driving over craters? It shouldn't do that. Is it driving towards howitzers, which are a threat? It shouldn't do that. Is it at least driving towards the command post? When combat happens, is the combat being resolved properly? Is the AI working the way it should? There's a lot of things that I needed to see kind of inside the brain of Python as it's playing the game. So the first thing we'll do is we'll give you a unit selection, and then it will give you a hex ID. So you could set the physical game up by putting these units at those hex coordinates. The next thing it will do is it will step through and show you the map. And I am representing the map as a 2D array with the hex coordinates. The craters are the little ASCII art that's on there. you can see the command post is right up here, CP. Here's a howitzer. The Ogre is on there somewhere, bottom right, you can see the Ogre. And this map, I overloaded the print method of the map. So to get this, all you have to do is say print map, which is kind of cool. And as it goes through and it checks the units, if a unit, the armor units can be disabled, which means they can defend, but they can't move and they can't attack. And on the following turn, they can recover. So what we'll call a good order unit is going to be all caps. Like this is horrible placement, by the way, to put your howitzers in the upper left-hand corner. But they're not disabled because they're all caps. If they're disabled, they would be lowercase. It would be HWZ in lowercase. So we can kind of get a snapshot of the game state at the end of a turn. And then this is an example of the fire phase for the defender. The howitzer is at that hex location, and it's looking for a target. It's decided to target the Ogre's main battery. And we resolved the combat with a CRT table. We got a D, which is no effect for the Ogre. So that lets us step through the game state. And then as the game moves on and the Ogre moves into range of other units, it looks like this game was played using only howitzers. And it looks like placement-wise, the Ogre maybe had to drive through them. And so all these howitzers are firing at the Ogre. And you can see the Ds are no effect, the NE is no effect. But every now and then you get an X, which is a hit, and it's taking tread off of the Ogre, and then that's going to be slowing the Ogre down. And then at the end, it will dump out some statistics for you. This ended in a victory for the defense. It took 12 turns, and you can see the Ogre was basically completely destroyed. All the tread were removed, knocked down to 0. You can't take away negative tread, but you know, there's some math that happens. No missiles remaining. They were either fired or they were destroyed before the Ogre could shoot them. No main battery, no secondary batteries. This is about as good as it gets for the defense. The only reason it wasn't a complete defense victory is that the defense lost too much armor knocking out the Ogre. So let's look at the training data. I arbitrarily decided that I would have the Python AI play 100 games, and that would be the training data. And then after 100 games, the genetic algorithm would start to work. And I wanted to play these 100 games 20 times so that they would be statistically significant. So I could learn what those random games look like. Because ultimately, AI doesn't matter if we can't do better than random. So what it looks like is that out of those 100 games 20 times, the minimum defender victory was 2 out of 100 games, which is pretty terrible. But the max was only 9. And I've got mean, median, and mode here, and in case it's been a while since you've taken statistics, there's hints in parentheses. But the mean, median, and mode were all about 5, which is a pretty good indicator that after playing 100 games 20 times, the average is probably 5. So that's, out of 100 games, as good as we can expect the defender to do without any artificial intelligence. Yes. And like I said, there was never a complete Ogre victory or a complete defender victory. And so that's an interesting question to look at too. So the interquartile range for this training data, this is the same thing I just showed you, but it shows you where those numbers lied. So if we look at the first quartile, Q1, 25% of the data was between 2 and 4. So the defender did not do very good. The blue box shows you the middle 50% range, and it also shows you where that mean is within that 50% range. So it's skewed a little bit to the low side. But the second quartile and the third quartile, like I said, are enclosed in the box, which is a range of 4 to 7. So somewhere in there, we expect the defender to win, on average, 4 to 7 times, with an average of 5. And then the high outliers is between 7 and 9. 25% of the victories were at that upper end of the range. And this is important because, like I said, we need to know if we can do better than random. And you guys have probably heard the quote from Mark Twain about statistics. It's worth repeating, I guess. There's three types of lies. There's damn lies, and then there's statistics. It's attributed to Mark Twain, but it's not really Mark Twain that said it. He attributed it to a British prime minister, who I won't try to pronounce his name. So this is the outcome of my experiments by running the Ogre AI simulator with machine learning and genetic algorithms. When we play 100 games, remember the genetic algorithm's not in effect. On average, there's 5 defender victories, and there's no improvement than that. That's random. When we do 1,000 games, we get 116 victories, and that's a 56% improvement over random. Better than half, which is pretty good. But as we run more games, as you can see, we run 10,000, then 100,000 games, the percent increase is really negligible. We don't really get much better by playing more games. So what this is showing us is, one, there's a law of diminishing returns, that once we've played 1,000 games, we probably have a pretty good idea of the right mix of units and the right behavior and how they should be placed on the board, how they should move, and how they should coordinate fire. Once we've played over 1,000 games, which a computer can do really quickly, by the way, we don't get much of an improvement. In fact, you can probably attribute this slight increase to just brute force of playing so many games. But it's not really learning anymore. So the questions are, how can we, once we reach this AI plateau in learning, how can we get above that? How can we get above that local maximum? So some things to try would be to add different behaviors to the units, other than brave, cowardly, and disciplined. We could tweak the behaviors of those 3 types. Maybe we could change the probability of targeting, or the targeting strategy, or the firepower ratio when they try to attack. We could modify the unit's behavior on game state. So a brave howitzer is always a brave howitzer. And that's not the best unit to use, because howitzers can't move anyway. It could be a cowardly howitzer and it can't run away. It's stuck there. But it will target stupidly, out of fear, I guess, right? So it can still be a detriment. But the point is that those behaviors are fixed at the start of the game. So as the game goes, maybe as the ogre gets closer to the command post, maybe those units could change. Maybe they could be emboldened to become brave from cowardly or disciplined. Or vice versa. Well, I don't know what the right mix is, but we could change those behaviors mid-game based on game state. That would be something we could try. And then we could also look at the genetic algorithm portion, and we could change the number of training games. We could change the probability of genetic mutation. We could change how we select games. There's a lot of different things we could do that we could modify and repeat the experiment and see if we do better once we begin to collect this base set of data. And so future work, how many games are enough? I think we know that. It's about 1,000. We never got better than a defense victory. We never got that complete defense victory. So we can experiment with ways that we could improve the AI learning for this. We could implement additional behaviors, like I said. Another thing is location does not matter in this. What I'm focused on is unit selection. So once you select those units, say you've got your units in your top 2 games are both the same in terms of the unit type and their values. They're all brave, or there's a mix of brave and discipline. When you go to play that 3rd game where you inherit those genes, the location might be different where it puts them out. It's going to put them out legally, but it doesn't currently track location. We could track location as a gene, and we might find that location does indeed matter where you put those out. It's just in terms of trying to get this all to work in one semester, there was a lot I had to do, specifically in terms of rendering the map to Python and teaching Python how to play the game. That took most of the semester. So that by the time the semester was over, there wasn't a lot of time left to experiment and try to do better. I did prove, I think, conclusively that it did learn and it did play better, but it did plateau and it never did get that complete victory. And automating the analysis would be really nice. When I set out to do this, I pictured the nice, visual analytics of the game, seeing the game state, and seeing the counters move and throw in sound effects. Why not? And since the AI is built in, you playing against the AI, right? So, but I had to scale it back a bit as I got involved and learned even just figuring out distance from the Ogre to the command post and optimally routing there is actually pretty complicated if you're new to Python or new to AI. But these are all areas for improvement in future work. You can email me at williamhutton@gmail.com. You can download and play with the code on GitHub. I've got about 15 minutes left. I've got some backup slides. We could also just call it good. You can grab something to eat, or we can take questions and have a discussion. So, see our hand raised? We're going to have a discussion. Okay, so the question was, what drove the Ogre behavior? I very simplistically implemented the Ogre behavior the same way every single time. The goal of the attacker is to destroy the command post. And the Ogre is tough enough that it finds the shortest route to the command post. If it gets within missile range and it has a missile, it'll shoot its last missile at the command post. If it doesn't have any weapons left, it has to drive all the way to the command post and run over it to destroy it. And then it tries to get off the board. So once it gets to the top of the board, it has to exit. So the Ogre, in that sense, is very dumb, because even if there's only one armor unit left, and it's disabled, so it's completely no threat to the Ogre will just drive off the map. It won't actively seek and destroy it. So the Ogre AI is fairly dumb, just to allow me to investigate the defense AI. And I saw a whole lot of hands in the beginning there.
So you said this was a term project for an Intro to Python class?
Yes, sir.
What grade did you get in the class?
So that's a great question, and I will share my experience with you on that. So, so this was the second time I'd taken a course from this instructor. I took an introduction to computer graphics class the first time, and in grad school, an A is an A, and a B is you did horrible, just so you guys know. So a B means you did pretty bad. I got a B- in the graphics class. And just so you know, I'd never done any graphics, and it was hard. It was a really hard class. And my term project for that class was to take grayscale images from, and in your academic career, you can go for the easy A or you can go for knowledge. And I really wanted to learn Python from this guy. He's a master. I did get an A in that Python class. Thanks. So I learned from my mistakes. But day one, I asked him. I said, I don't want to repeat the term thing, right? I worked really hard on that. I don't think I deserved an F, right? And he told me why I got an F. He said, you're supposed to do something new with graphics. You used 30-year-old satellite data to do a terrain height map, which is not new. Fair enough. He thought this was a great idea, and he also played Ogre. So, so he was interested in it. But, so that, long-winded answer to your question. And in the back, Mike's is coming for you.
I didn't hear, or I couldn't remember. The initial setup of the board, is that random, like when humans play each other?
It is not. So the Ogre comes in on the bottom row, and the defender can set up the majority of his units in the top third of the map. He can set up a certain number of units in the middle and none in the bottom. So it's not random, but if you get into statistics and probability, there's something in Ogre called the fuzzy-wuzzy defense and the 4 howitzer defense, Those are ways you can break the game with certain selections of units and playing them in a certain order. But I look at that as cheating. The GEV unit actually gets 2 moves. So it can move 4, and then it can fire, and then it can move 3. And so what it can do is it can kind of, if you take a swarm of GEVs, you can sort of swarm the ogre, target it, and then swarm out. And like bees, attack and run, attack and run. That's the fuzzy wuzzy defense. The 4 howitzer defense is a way of just setting up 4 howitzers with overlapping and interlocking fire. I still don't know whether you're supposed to target the weapons or the tread, though, in those instances. But they're basically viewed as broken strategies. That's why they say it breaks the game. It's a high probability, yeah. And there's still the randomness of the die, but you know, any game where you're rolling 1 6-sided dice for something that's a little unsatisfying, you know, you'd rather maybe see like a D20, even though the probability still might be the same, you know. But rolling a 5 or a 6, you know, it's hard. Any other questions? A few more?
Not related to this project explicitly, but you say you took the course because of this person's approach to Python. What did you learn about programming in Python from this person that most changed the way you thought about it?
That's an excellent question, thanks. So the biggest thing I learned really was, and I'll explain this, I won't just say I learned how to write Pythonic code and leave it at that, right? But you know, as a programmer, if you know other languages, it's not just, oh, I'll learn the Python syntax for a for loop when I can write good Python. Python has a very Pythonic way of doing things, and especially in terms of lists. It's very list-oriented. I would say, and he gave a lot of very difficult assignments throughout the course, too. And one of my favorite assignments was to implement a Roman numeral class. So to do arithmetic with Roman numerals. And that was pretty difficult. And what we were doing was overloading the magic methods in Python. If you look at Python, you can do dir, and it'll show you what the namespace looks like. And anything with underscores are magic methods that are things like add, subtract. So if you want to add 2 Roman numerals, and you want to add I, which is a 3, and another I, which is a 4, it's not just concatenation, because it's not I, it's IV. So you have to simplify. And I did a lot of that with those magic methods that we implemented for the Roman numeral class. The other thing I learned is that Python is pretty optimized. We did some other things where you'd count words in Shakespeare called, I think, concordances, but don't hold me to that. But I thought that my brute force procedural approach to Python would be good enough, but that the performance would be bad, and then I would have to optimize for performance. But it ran very fast. Like, it could read a whole work of Shakespeare in like 3 seconds and count each word on each page and count them and keep track of where they were. But really the largest thing I learned, without going into the individual details, was how to take the Python paradigm and apply it to problems and not solve problems like you would solve them procedurally or object-oriented. Solve them in the Pythonic way of doing it, which I don't think you necessarily get from a book on Python. And I saw, sorry, follow up? Oh, so the professor's name is Bob Lewis. He's at Washington State University, and he does have a book on Python coming out eventually. It's written, and we use that book in our course, but we got PDFs of the book, not the actual book. And it looks like, do we have about 7 minutes left?
No, we got to set up for the next one.
We're out of time. Okay. So I'll be around all weekend for the conference. If you guys have questions or want to talk Ogre or even play a game, come find me. Thanks.